Alright, so this section is pretty straightforward. It's just algebraic properties of what we can do with matrices. So multiplying, division, or the commutative property or associative property when it comes to addition and multiplication. And we'll see in a little bit of what we can do with most of them. And something eventually talk about the transposition or transpose of a matrix. But for now, we'll just do a major theorem of the addition property and the cumulative and associative property. So given three matrices A, B, and C where they all have the same rows and columns, an n by n matrix. So that means all of these are probabilities are true, meaning if I add A and B, it's the same thing as I flip them around, so the cumulative property works. And also the associative property also works. If I just do add A and B first, then add C, it's the same thing as just adding B, C, and A as well. Okay? That's a nice thing is, when it comes to addition, it works the same way as just like arbitrary numbers when it comes to matrices. Okay? And same thing applies for 3 and 4. So there exists a unique matrix Z that's called the zero matrix. So it's literally just a matrix, a bunch of zeros, kind of like that. Where if you add it to matrix A, you get the same result back because it makes sense, right? You're adding 0, you get the same result no matter what. Okay? And the last given scenario is given a matrix A with, but that's an m by n, and there's a unique another m by n matrix P such that when you subtract them, you get the zero matrix. Okay, so I know when it comes to numbers, we have the opposite or the inverse. We'll talk about that more precisely what it is, but basically saying there's a matrix P that if just the opposite sign, you add them together, that gives you the zero matrix, which makes sense. So it holds under operations of the zero matrix. We'll talk about that later on as well. But the biggest thing about this section is going to be a lot of proofs and how to break this down and how to show, or let's say introduce a proof and how it's actually applied into it. Okay, so we're going to prove the first property in this theorem, that AB equals BA. So how you want to actually start these type of proofs, especially when it comes to linear algebra, is start with basically what the theorem tells you. So that A, B, be n m by n matrices. Okay. Now there's two different ways to do this proof. You could do it the old-fashioned way, or you could do the, I guess, like proper or high level skill wise. So since we're learning this stuff, I'll show you the long way, which is going to give you the correct answer, and then I'll show you guys a little shortcut if you understand the properties of a matrix. So how this goes, since we have A by, so we're just going to do A plus B. Okay, so right, this is an arbitrary m by n matrix. So matrix A is just going to be these matrices, or it's this matrix. And then you're going to add it to B, which is the exact same matrix, but now different entries. So remember, when you add matrices together, you just add entry to entry. Okay, so again, in this case, you can now split this up if you want, or you could just go the opposite and show that this side does actually equal this portion here. So I'm going to just do the other way. So I'm going to start here and just rewrite it. And how I'm going to rewrite it is just simply just flip these around. Since addition is cumulative, I can flip everything around I want. So now the B's will be in the front and the A's in the back. Okay. Well, now if I split this up, this is technically matrix B with this entry. Plus A. So this is B plus A. Okay. So that's the long way, and when it comes to all these proofs, this will always work out kind of nicely. It might take a while, but it does make sense, right? You add each entry, then you just flip it around, and then you split them up. It gives you that. The alternative, and you're going to see that in a little bit when we do the next one, is using the actual notation of a matrix. So you said let A, matrix A be any arbitrary entry, and let B, matrix B, have any arbitrary entry there. So now when you add A plus B, that's adding component to component. Well, just like I did here, I could flip this around. Which gives you B plus A. And there you go. So a little shorter version, but this understands it, knowing what a matrix is and knowing that all we're talking about is the individual entries themselves. And this is an arbitrary entry within this matrix going forward. Okay? But again, this will work anyways. Okay? So that's the addition part. Now let's go into the multiplication part. That's the next two theorems. So theorem 8 and 9 basically mean exactly that. So theorem 8 is about scalars. So given three arbitrary matrices with these rows and columns, then under multiplication, this is true. So the associative property ratio holds for multiplication. Okay? If R and S are scalars, same thing applies for itself. I can first multiply the scalars themselves, then multiply by the matrix. And same thing for number 3 is vice versa. So if this is a scalar, I could bring it however I choose. I could bring it to the front, to the middle, or to the or multiply by the very first one at the end. Okay. So kind of food for thought for there, right? Now, theorem 9 puts the first theorem that they're made together is addition and multiplication. So they're basically like the distributive property, if you remember that. So given A and B are n by n matrices and C is a arbitrary n by p matrix, which means we can actually multiply them together. Therefore, this is true. Okay, so basically I could distribute, but the problem with the distributive property is, unlike when it comes to numerical values, it has to follow the same format, meaning if it's on the right-hand side, it's going to be on the right-hand side of the matrix, not on this side. Okay. Same thing applies for 2. It's just the opposite. So if A is on this side, I could distribute. But again, you're going to multiply A by on the left-hand side because it started with the left side. And then 3 and 4 are about the same as 2 and 3 up here with scalars. If I have two given scalars, I first add them times A. I can distribute the A however I choose because they're just scalars. And vice versa for number 4. If R is a scalar, I can multiply A to B however I choose itself. Or I could just first put A and B together and then multiply by R. Okay? Whichever makes it more easier to deal with itself. Okay? Now, let's talk about this proof here. So we're going to prove 8-1. So this one right here. So ABC is equal to ABC with the parentheses respectively in both cases. Okay. So this one, it would take you a long time and a while to do it this way. And I actually, it would be a nice good exercise to do so you get comfortable how to do the proofs, or, so you can see this format. So I'm going to follow this format just because of time constraints and this length. But it's a good format just to try this out. Do this the long way so you can see how it would work out itself. Okay? Right, so just like every other proof, I write down what I'm given. So I'm pretty much given what the first term says up to here, right? So let A be a m by n matrix, n by n, B be a n by p, and C be p by q matrices. Okay, so we're going to go this way itself. So I'm going to show this side equals this side. So I'm going to follow this part. Okay. Now, to do this process, you have to go back to what it meant to be when you multiply matrices together, right? So remember, when you multiply matrices, it's row by column, and you times each entry, and then you add the entire row together, gives you one entry in the matrix, right? So the actual notation for that, if you go back, would look like this. So it's the sum, right, because we add the results together of the multiplication of the entries. So that's the definition of matrix multiplication, right, the actual sum of it. Okay, so that's A times B. So this is what's in the parentheses. Okay, so now we're going to multiply by C. Okay. All right, so on the border here, I'll put let A equal A, J, K. Let B, 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 K, J. And let C, B, C, J. What's a letter? We'll say R. Okay. All right, so now when I do A, B, and then C out here, I'm going to follow this template. But remembering that this part here is there. So I'm just going to copy it down. Okay. And now I'm going to be multiplying by the C term. And again, by definition of a multiplication of matrices, it's going to be the sum of this matrix times this matrix. So you can think of this as one whole matrix. So it's easier to do with this notation purposes, you call this like D itself. So this could be J equaling 1 to N. Okay. So now at this point, just remembering a couple of properties of summations is if I have the double summation, I could just drop the parentheses and just simply have the double summations. Okay. So what I'm going to do now is I'm going to take, let's see, this one right here is represented as J, so I'm going to put this right in between them because this one has this and this in common here. So remember, I'm still multiplying, right? So nothing has changed there. I'm just maneuvering it however I choose, because remember, at this point within this, I can move stuff around because I'm just multiplying a value itself together, right? Especially when it comes to also these summation notations by using the properties of summation. So this will now be on the outside. And then we put this A here with it. And then times, and put the summation right here. And again, I could do that because these two are dependent on the J term. Okay, so now I revert back to multiplication. So what is this saying? Again, this is saying A times P, right? So this is A, B, and C. So what I'm doing is I could first multiply this together and then times it by the summation of A. So this is just A on the outside and then B times C on the inside. So very theoretical, totally understandable, when it comes to these kind of proofs going forward as well. Okay. All right, so let's try another proof. So we're going to prove theorem 9.1, so which is this one, the associative property or distributive property on the right-hand side. Okay. So again, I do suggest trying it the long way. This one actually works out not bad. Not too bad because you just show one side does equal the other side, just doing both. But again, I'll try doing the notation ways just this for the sake of time here in space. Okay. All right, so let me get my notes here. So just like everything else, we're just going to write down what's given to us. So in this case, we are given, so let A, B, B, M by N matrices, and let C be a N by P matrix. And then the same thing, we'll let A equal A, I, J, and let B equal B, and they're both M by N, so be I, J, and then let C equal C, J, R again. All right, so these are the same because they're both the same n by n matrix. So it's going to be the same entries in both categories we're talking about. Okay, so we want to show this just in case you want to go backwards. Okay, that's our goal. Okay, so first we're just going to add the entries together. So A plus B is just the sum of these two, so just Aij plus Bij. You're just going to add up each entry together. So nothing too difficult there. Okay, now and I'm going to put this in parentheses there. And now I'm going to do multiplication. So we're going to use the same property as loss of proof of the definition of multiplication. So this is equal to the sum of that. Okay. Yeah, that's my wish. Okay. Okay. All right. So now I'm going to move this stuff around. So again, this is just entry to entry now. And again, this is an arbitrary number. This is an arbitrary number, and this is just multiplication with it. So because we're dealing with numerical values now, I could just distribute this. And this still works because these matrices are still going to be going each other's way. Again, we'll put this in parentheses. Okay, and again, because there's a plus, I can split this summation up into two summations. Okay. So again, knowing what this represents, so this is the product of A times matrix C plus, and this is the definition of B times C. And then we got it. Okay. So after a lot of proofs, let's do a nice definition. So this is actually a little bit new to us, something called a transpose. So if A is some arbitrary matrix, n by n matrix, then the transpose of A, denoted as A with a capital T above, like little power, is the opposite. You just flip the entire thing around. So now it's an n by m matrix. So you just swap the rows and columns together to make it look like this. Okay? Where again, every entry is literally just swap position of the nth by n matrix itself. Okay? So again, there the definition is kind of funky. It's probably much easier to just go by an example. Okay? So let's find the transpose of each one. So make it easy, right? You're going to swap it. So this is a 2 by 3. So the transpose is going to be a 3 by 2. Okay. Now, how this works is you just literally swap places. So instead of going this way, it's now going to be going this direction. And the entire row here now becomes a column. And the same thing applies for the other case. So since this is the first row, it's going to be the first column. Just like that. Okay. So now let's try B here. So now what if we have a 3 by 3? Well, we still get a 3 by 3. But again, we're going to follow the same template. So first row becomes the first column. So this one becomes the second column. And then finally the third. And there we go. That's how we do transposes of matrices. Okay. So because we have this new definition, well, that means we can now apply it to old stuff, right? So in other words, the old theorems we just talked about. And that's what this is all about. So let A be n by m matrices, and let C be, again, n by p matrix. Then all these three are true, based off the transpose of them. So I first add them together. Transpose it is the same thing as if I distribute the transpose each one. That's an interesting one, actually. 2. This one's actually I got to be careful of. Unlike over here, it doesn't fall on distribute. You also have to flip the matrices and make it true. And one that's probably obvious, the transpose gives you the back. So it would make sense, right? If you do opposite, it gets you back to the original itself. So again, nothing too crazy, but this is actually one you got to be very careful of because it's not a straight distributive. It's a distribute plus and also a flip of the matrices. Okay, so let's going to do proof of theorem 1 here. Okay. So like everything else, so let A and B be M by N matrices. Okay. Well, I'll start from here. Okay. So A plus B is going to be, I'll do this as well. Okay. So then A plus B is going to be Aij plus Bij. Okay. Now, unlike the other ones, I'm going to define one extra thing. Okay. I'm going to say the sum of A and B of each individual entry is going to be, again, it's an arbitrary number, so I'm going to call that C of Ij. Okay. So this is now going to be Cij, one single number, which makes sense, right? This is one single number. We'll just call it something else. Okay. So now what we're going to do is we're going to do the transpose. So A plus B transpose means I now transpose this. Now, what is the transpose of this? Well, according to the definition, everything just swap places. So now this becomes C of Ji. Okay. Okay, but this was the sum of a number, right? Defined to be the sum of these two put together. So if I break this part, well, this sum is now just the sum of AJI plus BJI, right? That entry in this matrix itself. Well, again, by definition of our transpose, which is right here, this also is the definition of A transpose. And this is also the definition of B transpose. And there we go. We proved number one. Okay. All right. So, did a lot of work, a lot of proofs. Let's go now to actual applications, shall we? All right. Now we're done with the proofs for a while. So, first definition here is a matrix is symmetric if A equals its transpose. That's what's called a symmetric matrix. Now, a little side note just for know-it-all. A matrix A can only be symmetric if it's a square matrix, meaning an m by m matrix. So 2 by 2, 3 by 3, 4 by 4, 5 by 5, and so forth. So this is a little sidebar there no matter what. If first has to have this, then you're going to check it. If it doesn't have this, it's automatically never going to be symmetric. So fun little side note there itself. Okay. So here are some examples of a symmetric matrix. Like that. Okay. So if you do the transpose of this one, we get the same thing. And also for B. Oh, this one. So this would not be a 1. So this will be a yes, and this will be a no. Okay. So pretty straightforward, right, when it comes to it. It's identically the same. It is. It's not, right. This is very similar, but they're not exactly the same. And that's the key thing. All right, so now let's identify something that we're going to talk about a lot in this class. It's called the identity matrix. Okay, so the identity matrix I is an n by n matrix, so it's a square matrix in which the main diagonal entries are 1s and all the other entries are 0. Now, we've already talked about this a little bit, and it's basically our goal when it comes to solving for a system, but now we're actually talking about much more in depth. So it kind of looks like this. So where all of these are just 0. So if you want a 3 by 3, the identity matrix will just be this. That. So that's called the identity matrix, and then much more in depth later on. But now, to finish up this part, going back to a little bit of how does this incorporate to three-dimensional space, and more importantly, a multivariable calculus, which is, I'm pretty sure, everybody's favorite class to begin with, is given two vectors in R3, x and y. So given transpose of t is equal to that, okay? So therefore, if I do the transpose of x times y here, this gives us this part. Right, that's how it would look like unit by unit. So this would give me something I'm pretty sure you guys are, well, more precisely of. This is the dot product. So now what we can do with vectors, if we can find the dot product, we can do everything we did in multivariable calculus now with matrices to a certain extent, but for now just basic formats. And the main one we can do the most of is norm of vector, right, or length of vectors. So now we can do length of matrices. So in general, given two vectors in Rn, So the product is the dot product, like I said, of two vectors. So going back to multivariable calculus, we can now find the length of the vector. Now, more precisely, when we talk about Euclidean space or so another name for this is called Euclidean norm, or Euclidean length of it is given to be this, which is going to be our main focus. So it's the transpose of the vector times its original vector within the square root. Or another way, if you want to find the difference or the distance between two vectors, this is how we define it, which is the same thing we did in multivariable calculus, right? So to finish up this section, I'm going to do a practice problem illustrating these two definitions. So let's suppose vector x was 2, 1, 3, and y was -2, -1, and 3. Okay, so we're going to do each individual one. So we're going to find this dot product, that length, and the distance between them. Okay. All right. Step one. So this is going to be basically the dot product. Well, it is the dot product actually, right? So 2 times -2, 1 times -1, so -1. And then finally, 3 times 3 is 9. So this is going to be -5, so it's going to be 4. So that's our dot product. Okay. Now we're on to 2. So 2, we just want to find the length of x. So the length of x is just going to be defined by this portion. So it's just going to be transpose dot product its original vector. So 4 plus 1 plus 9, so 14. And since we want the length, so it's going to be the square root of 14. And now we do the same thing, but for y. So 4, +1, and also 9. So this time again gives you 14. So the square root of 14 again is the length of the vector. And then finally, the distance. So for that one, we first subtract them and get the transpose, subtract them, and then basically get the dot product of each one, right? So when you subtract x minus y, so we just go straight across. Okay. All right, let's see what we get here. Okay. So we get 2 minus a -2, so that's going to be adding, so that gives you 4. 1 minus a -1, so that's addition, that gives you 2. And 3 minus 3 gives you 0. Okay, so that's this part. All right, so the transpose of this would just be 4, 2, 0. So now I'm just going to make the dot product of this, so I'll just put it all together. So 16 plus 4, so 20. So the distance is going to be the square root of 20. Okay, and there we go.